1600 years ago, St. Augustine wrote something that still haunts me. He said, "What is time? If no one asks me, I know. If I want to explain it to someone who asks, I do not know." I have spent 50 years as a physicist. I have worked with equations that contain time as a variable. I have measured time with atomic clocks precise to billionths of a second. I have proven that time slows down for fast-moving objects and near-massive bodies. I have thought about time more deeply than most people ever will, and I still cannot tell you what time is. This isn't false modesty. This isn't a rhetorical device to make the video more interesting. This is the honest truth. Physics uses time constantly, obsessively, in every equation and every prediction. But physics does not explain what time actually is. We treat time as a given, as a background, as a stage on which events unfold, but we never explain the stage itself. Today I want to take you through everything we know about time, everything we think we know, and everything we don't know. I want to show you how our understanding has evolved from Newton to Einstein to quantum mechanics. And I want to be honest with you about where that understanding stops, because time is not just an unsolved problem, it might be an unsolvable one. Let's begin with what we thought we knew. For most of human history, time seemed obvious. It flows, it passes. It moves from past to future like a river carrying us along. Yesterday is gone. Tomorrow hasn't happened yet. Now is all that exists, a moving spotlight illuminating one moment after another. Isaac Newton made this intuition mathematical. In his Principia, published in 1687, he wrote that absolute true and mathematical time of itself and from its own nature flows equably without relation to anything external. Time was universal. Time was constant. Time was the same for everyone, everywhere, ticking away at the same rate whether you were on Earth or on a distant star. This felt right. It matched our experience. When I look at my watch and you look at yours, we agree on what time it is. When we say something happened at the same time as something else, we assume that phrase has a definite meaning. Newton's absolute time was the scaffolding of the universe, unchanging and eternal. Then Einstein came along and demolished it. Did you know time is an absolute? In 1905, Albert Einstein blew everyone's minds with his theory of special relativity. He showed that time is relative. The faster you move, the slower time passes for you compared to someone standing still. This isn't just a theory, it's a proven fact. We see it in particle accelerators and even in the GPS satellites orbiting Earth. They have to constantly adjust for this time difference, or your phone's navigation would be off by kilometers every single day. Imagine you flew in a spaceship at 99% the speed of light. For you, 1 year might pass, but when you return to Earth, you'd find that 7 years have gone by for everyone else. You literally aged less because you experienced less time. This means there's no universal now. My present moment is different from yours. Mind-bending, right? Thanks for watching. And don't forget to subscribe for more amazing science. If time doesn't flow uniformly, if different observers have different nows, then what is time? Einstein's answer, and the answer of most physicists who take relativity seriously, is something called the block universe. Imagine the universe not as a three-dimensional space evolving through time, but as a four-dimensional block. 3 dimensions of space plus 1 dimension of time, all existing together. In this picture, the past isn't gone, the future isn't unwritten, they're both there, built into the structure of the block. Think of a movie reel. When you watch a movie, you experience it 1 frame at a time. Frame 1, then frame 2, then frame 3. It feels like the story is unfolding, like the future frames don't exist until you reach them, but the entire reel exists. Frame 1000 is just as real as frame 1. It's just located elsewhere on the reel. Your life might be like that. Every moment from your birth to your death exists as a frame in the 4-dimensional block. You experience them sequentially because that's how consciousness works. But the frames are all there. Your first memory is still happening. In the region of space-time we call the past. Your last breath is already there. In the region we call the future. Einstein believed this. When his lifelong friend, Michel Besso, died, Einstein wrote to Besso's family, "Now he has departed from this strange world a little ahead of me." That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. He wasn't being metaphorical. He was being precise. In the physics he helped create, time doesn't flow. The block just is. But here's the problem. If the block universe is true, why do we experience time as flowing? Why does the present feel special? Why do we remember the past but not the future? The block is static. Nothing moves through it. Yet we feel like we're moving through it, carried along by some invisible current. Physics has no answer to this. The block universe describes the structure of time. It doesn't explain our experience of time. And that gap between structure and experience is one of the deepest mysteries in all of science. Even if time doesn't flow, it certainly has a direction. The past is different from the future. We remember yesterday, but not tomorrow. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. There's an arrow pointing from past to future, and the universe respects that arrow. But here's something strange. The fundamental laws of physics don't contain this arrow. Newton's laws work equally well forward and backward in time. If you film 2 billiard balls colliding and play the film in reverse, the physics is still valid. Maxwell's equations for electromagnetism are time-symmetric. Quantum mechanics is time-symmetric at the fundamental level. The basic equations don't care which direction time goes. So where does the arrow come from? The standard answer is entropy. The second law of thermodynamics says that entropy, a measure of disorder, tends to increase over time. A neat room becomes messy. A hot cup of coffee cools to room temperature. Concentrated energy disperses. This is the arrow of time, and it's statistical rather than fundamental. It's not that the laws forbid entropy decrease. It's that entropy decrease is overwhelmingly unlikely. But this answer raises another question. Why was entropy low in the past? If the universe tends toward disorder, why did it start in such an ordered state? The Big Bang was an incredibly low entropy condition, a hot, dense plasma remarkably uniform in temperature and density. That's a very special initial state. Why did the universe begin that way? We don't know. We can describe the Big Bang. We can calculate what happened afterward, but we can't explain why the initial conditions were so special. The arrow of time points away from that special state. But we don't know why the state was special in the first place. And there's an even deeper problem. Even if we explain why entropy increases, we haven't explained why we experience time flowing in the direction of entropy increase. We haven't explained why consciousness is oriented toward the future rather than the past. We haven't explained why the present feels like now. Entropy gives us an arrow. It doesn't give us the experience of following that arrow. Now let me tell you about something that might disturb you. In the most fundamental equation of quantum cosmology, time doesn't appear at all. The Wheeler-DeWitt equation is an attempt to describe the quantum state of the entire universe. It combines quantum mechanics with general relativity at the cosmological scale, and it has a shocking feature. There's no time variable. The equation is static. It describes a universe that doesn't change, doesn't evolve, doesn't flow from past to future. The wave function of the universe just is. It doesn't depend on time because time isn't in the equation. What does this mean? Some physicists like Julian Barber take it seriously. They argue that time is not fundamental. Time is an illusion that emerges from a deeper, timeless reality. The universe is a collection of configurations, frozen moments, and what we call time is just a way of organizing those moments in our minds. In this view, the flow of time is like a movie created from still frames. The frames don't move. The motion is in the viewing and the consciousness that experiences them sequentially. But the frames themselves are all equally real and equally static. Other physicists reject this interpretation. They argue that the Wheeler-DeWitt equation is incomplete, that time will reappear when we have a better theory of quantum gravity. They might be right. We don't have a complete theory of quantum gravity, so we can't be sure what the final picture will look like. But the Wheeler-DeWitt equation is a reminder of how poorly we understand time. At the deepest level of our best physics, time disappears. Either it's an illusion or our best physics is missing something fundamental. Both possibilities are disturbing. Science fiction loves time travel. So do physicists, in our own way. What does physics actually say about traveling through time? Traveling to the future is not only possible but proven. Special relativity guarantees it. If you travel at high speed relative to Earth, time passes more slowly for you than for those who stayed behind. When you return, you've traveled to the future. Everyone else has aged more than you have. This isn't speculation, it's confirmed physics. The effect is small at ordinary speeds, but it's real. Astronauts on the International Space Station age slightly less than people on Earth. Particles and accelerators live longer than they would at rest. Future time travel is a matter of engineering, not physics. Other solutions involve wormholes, cosmic strings, or rapidly rotating black holes. But these solutions seem to require exotic conditions that may not exist in our universe. And they create paradoxes. If you travel to the past and prevent your parents from meeting, how were you born to make the trip? The grandfather paradox suggests that something is wrong with past time travel. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel to the past. Perhaps quantum effects destroy any wormhole before it can be used. Perhaps the universe protects causality by making past travel impossible. We don't know. The physics is unclear. But what time travel teaches us is that our intuitions about time are unreliable. If physics even permits discussing time travel, then time is stranger than our everyday experience suggests. Let me be direct about what we don't understand. First, why does time have a direction? We can describe the arrow of time using entropy, but we can't explain why entropy was low in the past. The initial conditions of the universe remain mysterious. Second, why do we experience time as flowing? The block universe is static, but we feel movement. Physics describes structure but not experience. The flow of time might be an illusion, but we don't understand the illusion. Third, is time fundamental or emergent? The Wheeler-DeWitt equation suggests time might not exist at the deepest level. But if time emerges from something timeless, how does that work? We don't have a good theory. Fourth, how does time relate to consciousness? We experience time through consciousness, but we don't understand consciousness either. Two mysteries intertwined, neither one solved. Fifth, what is a moment? What is now? Physics has no special role for the present, yet consciousness seems anchored to a present moment. What makes now different from other times? These aren't questions waiting for better equipment. They're questions about the foundations of physics. And foundations are hard. We might need new concepts, new mathematics, new ways of thinking that haven't been invented yet. Or we might be hitting the limits of what science can explain. I started studying physics because I wanted answers. I thought that if I learned enough equations, understood enough principles, I would eventually understand what time is. 50 years later, I understand the equations. I can manipulate them, predict with them, teach them to students. But I don't understand time. Augustine was right. When no one asks me what time is, I know. I look at my watch. I see it ticking. I feel moments passing. But when I try to explain what's actually happening, what time actually is, words fail. Equations fail. Understanding fails. Maybe this is a temporary failure. Maybe in 50 more years, physicists will have solved the puzzle. Maybe quantum gravity will explain everything, will show us how time emerges, why it flows, what the present moment is. I hope so. I'd love to be proven wrong, to have someone explain time to me in a way that finally makes sense. But I suspect the mystery might be permanent. Time is the medium of our existence. We live inside it the way fish live inside water. Maybe we can't understand time because we can't get outside it, can't look at it from the outside, can't see it as anything other than the invisible context of everything we think and do. And maybe that's okay. Not every question needs an answer. Not every mystery needs a solution. The universe is not obligated to be fully comprehensible to creatures who evolved to find food and avoid predators. We've done remarkably well understanding physics, chemistry, biology, cosmology, but some things might remain beyond us. Time might be one of those things. Look at your watch. It's ticking. Seconds are passing. You feel the present moment, the flow, the arrow pointing toward the future. All of that is real. as real as anything you've ever experienced. But what it is, why it exists, how it works at the deepest level, these remain open questions, perhaps the deepest questions of all. Augustine asked 1600 years ago. I'm asking today. Physicists will probably still be asking in another 1600 years. What is time? I don't know. And that might be the most honest thing a physicist can say.